Morning, everyone. Can somebody just give me a thumbs up and just let me know whether you can hear me properly. Alyssa, there's an echo. Morning, everyone. Can you hear me online?
Yes, we can hear you clearly. Thank you.
Thank you so much. Thank you. Just sharing my screen. Right, thank you. So good morning to everyone online and everyone here in person with me today, to the last day of the Infectious Disease Modeling through Mathematics and Machine Learning workshop. Today's focus is basically machine learning modeling. That's in essence what it comes down, and this obviously includes a variety of different components. There are three speakers today. I will be the first one, and I'll be focusing on specifically supervised machine learning. So we're going to look at some methods of regression, multi-class classification, ensemble learning, and a little bit on neural networks, but it's an extremely broad field. So you can imagine there's a lot of information that I'm either not going to touch it or barely touch on. So this is basically just giving you a sense of the kinds of topics that are out there, the kinds of things that you need to engage with if you want to be able to really understand the field. So with supervised machine learning, you're basically looking at something that provides you with an output that you are aiming to target. So you are setting up a specific kind of algorithm, and you're saying to it, look, given these kinds of inputs, I want you to learn how to be able to target this kind of an output. So whether it's trying to predict whether the market's going up or down, and you say to your learning algorithm, look, these are the different kinds of features, this is the different kind of information that you need, and knowing this, you should be able to tell me if the market is going up and down, for instance. Now, even within that context, there are two different kinds of methods we're looking at. One is classification, and the other one is regression. So classification, usually pulled apart into binary and multi-class classification. Binary classification naturally being whether you're saying yes or no, or 1 or a 0. So just in essence, two options for the classification outcome. And then multi-class classification naturally means that there's more than two classes in which you can categorize your outputs. Now, regression occurs basically when you're trying to predict a continuous target variable. I think this is one in which we're all very, very comfortable with. So it's usually quite easy to know exactly which one of these two kinds of problem structures you're working with. Now, there are a variety of different kinds of methodologies which fall under this kind of a learning system, all right? Typical examples we're working on is like spam classifiers, facial recognition for images, medical diagnosis systems. There's many different kinds of problems across the world that are being considered within this kind of learning framework. But in essence, what you're doing is that you're saying that you have training data, so a collection of data points, X, Y, and the goal is to produce a prediction Y star for some response, some X star input, all right? And your inputs can be of a variety of different data shapes. So for instance, on Tuesday, we looked at different kinds of variety of data structures, whether it's images, signals, text, numerical. So this obviously completely depends on the problem structure, but the idea is that these kinds of learning algorithms are actually able to adapt and work with either one of those kinds of data inputs. Now, supervised machine learning systems generally then give you your prediction by some kind of a map. And fundamentally, that's what this comes down to. This entire process is a mapping exercise. How do you map information you have to the information that you want so that you can answer a certain kind of question? And the different kinds of mappings that exist are extensive. So we've got linear, logistic, decision trees, support vector machines, natural neural networks. And the structure can be very, very different in nature, usually underlying some kind of specific way of understanding the data or overlaying a framework in terms of how that information can lead to be able to gain certain kind of output. Now, before we actually go into the different kinds of models that exist, there's certain things that are extremely important to remember. Certain key ideas, like similar to your exploratory data analysis, which we discussed on Monday, you need to be aware of, you need to work through in order to be able to get a very good output there. One of these is over and underfitting. So if you want to be able to assess the quality of the mappings that you've created, you need to be able to assess the degree of over and underfitting that's happening. So in essence, what we're talking about is generalizing, getting your model to generalize well. That basically means that the model is very good at being able to look at a set of input it's never seen before, and then give you a very good outcome, very good prediction. All right, so the model's performance is in essence going to rely heavily then on its ability to be able to generalize well. And this is where the ideas of over and underfitting come in, because this basically tells you how well your model is doing. So for instance, imagine for instance that you have a classifier and it's 100% accurate on your training data set, all right? So when you're training it and you're teaching it, it gets it right 100% of the time. And then all of a sudden, you go to a test data set, another data set it's never seen before. You test it on that, and then you get a 50% accuracy. Now what that refers to, that situation means you've overfit. You've basically made your model understand that training set so well that anything that's remotely different, it doesn't know how to perform well on. So, and how can you identify this idea of overfitting? Well, you're looking at a generalization error. So this is the expectation of your model's error, where you apply to an infinite stream of additional data points drawn from the same underlying data distribution. So you're basically estimating your generalization error then by applying your model to your independent data set. So it's that data set that's never seen before. And when we apply it to that, we're getting what is termed our generalization error. And this error can then be pulled apart into two components. And these components are what's going to help us understand over and underfitting. Now, the first component is called variance. And this is the tendency of a model to learn random things, irrespective of what's the real signal. And this is then closely linked to overfitting, all right? So it then starts to think it knows more about the data in essence than it actually does. Your bias refers then to a learner's tendency to consistently learn the same wrong thing. And this is close to underfitting, all right? Now, I just have a quote here from Pedro Domingos, who said that strong false assumptions can be better than weak true ones, because a learner with the latter needs more data to avoid overfitting. All right, so the reason why I have this quote here is because you need to understand that the notion of overfitting or underfitting can actually be influenced by multiple different decisions that you make throughout your structuring of your machine learning model, and you need to be aware of this. So now, in an attempt to avoid your overfitting, which is in essence your variance, you may easily then adjust in a way that brings in too much bias, and then you this starts leading to underfitting. Now, underfitting occurs when the machine learning algorithm basically cannot capture those patterns. It just can't seem to look at the data and understand, okay, these are the things that are linking things across the board. So it doesn't fit the data well, and so it has a low variance, but very high bias, all right? So an example of a linear learner is, for instance, it has a very high bias, because when the distinction between the two classes is in a hyperplane, then the learner isn't able to induce it. So basically, it doesn't have the capacity to understand the pattern that is there. Decision trees, though, are actually quite different. They learned on different training sets. If they learn on different training sets, for instance, generated by the same kind of phenomena, you often have very different kind of output, even though in fact they should be the same. All right. Now, there's what's called the sweet spot. And this is where that interaction between your bias and your variance comes into play. The idea is that in your sweet spot, which I'll define now, is where you know what the true model is. So given an infinite number of data to calibrate it with, this is where you should be able to ideally reduce your bias and your variance to zero. That's what you want. That's not going to happen, all right? Because your data is finite, your models are imperfect. So there's a trade-off between minimizing the bias and the variance, and that is where that sweet spot comes in. And the sweet spot for any model is basically the level of complexity at which the increase in bias is equivalent to the reduction in variance. So if your model complexity exceeds the sweet spot, which we'll see in a visual on the next slide, we are in effect overfitting our model, whereas if your complexity falls short, then you're underfitting. And this makes sense, where if your model is so complicated that it's trying to take into account every single component that's in your data, it's going to understand that data set so well that anything outside of that, it really just can't relate to as well. Whereas if your model is not complex enough, it's not unearthing all of that information, and that's where you're underfitting. So here, for instance, is a visual representation of this, where you're looking at, if you look at the blue line, the one that's next to the block that says variance, you'll notice that at very low model complexity, you have very low error, right? When it comes to your variance. So the variance, remember, this has got to do with your ability to overfit. Now, obviously then, as your model complexity increases, because you're overfitting and your model complexity has now increased, you're understanding too much of that data set to the extent that there's no ability for your model to adapt to anything different. And you'll notice the exact opposite when it comes to your bias, for instance. That when your model has got a very low complexity, the error is extreme because it's not at all able to understand anything from your data. It needs an increase of model complexity in order for it to be able to not underfit. And then you've literally got in the center is where you've got your sweet spot. So that's basically where you want to lie with your model structure. Now, data structures. Since Monday, you've been hearing all of us that have been talking about the data or the machine learning, talk about the different kinds of data structures that exist. Imagine you have a data set comprising of like D observations, for instance. You want to be able to create some kind of prediction from that. You do need different data sets that function for different purposes. So in essence, what you'll do is that you'll have a certain data set that you'll be training your data on. So this is the sample of the data used to fit the model. And it's structured from specific instances of the attributes or features. So this is the actual data set you're using to train. And this is then going to be completely separate. Let's say that that's equals to N observations being used specifically for the training data set. But now there's also what is termed the validation data set. Now a sample of the data can then be used to provide an unbiased evaluation of a model fit on the training data set while tuning your hyperparameters, which we will discuss at a later stage. So there's certain parameters in your model that are important, and you want a data set on which you can train to get the best values for those without yet testing your model properly. All right, and that's what this validation set is used. So you train your model, and then you're basically testing it on this tiny data set to see which parameter values for this machine learning model are best. And that's what you're using here. Your test data set is then the final set that you're using to test your model that you've now created with your optimal hyperparameters. All right. So this is a sample to provide an unbiased evaluation of a final model fit for the model that you've been able to design. And now you can actually then evaluate your models. So if you've created 5, 6 different models, this is the test data set where you're going to finally say, okay, which one of these is the better one? Generally, this is a very well curated and contains carefully sampled data. And it spans various classes that the model would face. So the idea is that this test data set should represent the real world as well as possible, so that you get a true understanding of how well the model performs. Now, there's definitely a relation between the model complexity and the data set size. Okay, and there's basically a byplay between the size of the training and testing data sets and then the consequential accuracy of the model. And this then relates to the notion of the complexity of your model. Now, it is questionable whether increasing the amounts of data will improve the performance when one isn't applying a more complex model. So for instance, with linear classifiers that are trained on millions of specific features, can outperform more elaborate models that try to learn general rules. So you can often find that a more complex model does need a smaller data set to be able to perform well, or you could find that a very simple model with large amounts of data sets performs exceptionally well. But again, this is the kind of thing that it's not set in stone. Here is just what is termed your learning curve, just to give you a visualization of, in essence, what you're trying to see. If you obviously zero data Z means infinite error, obviously. But as your data set in the bottom on your x-axis increases, the idea is that the prediction error caused you to overfitting and underfitting, in essence, will actually start to eventually converge to a plateau. So the idea is that you're basically reducing your bias and your variance So the testing and the training error that is incorporated to be able to reach a kind of like equilibrium. So there are two different kinds of notions of complexity. It's not set in stone. The first notion refers to the number of free parameters in the model. And the other one refers to how complicated the model is in a more intuitive sense, kind of how elaborate is it. In this one, we may say that an algorithm that is not elaborate is basically described as a simple algorithm. So if you think of just a linear regression, that's usually seen as like a simple algorithm, because it's very basic in terms of our ability to understand it. So linear classifiers, even if they're high dimensional, they're not deemed elaborate in that sense. All right. So that's just to give you an understanding of how overfitting and underfitting have a huge impact on the model design and on how you need to assess your model. Other things that also are important is your data set structure, which is why I discussed the different kinds of data sets that you have, your testing set, validation, and training. But then within that, there's also the complexity of unbalanced data sets. Now, I'm not going to go into detail. There's a lot of information out there on this. But basically, just to remind you, firstly, not to confuse it with outliers. So an unbalanced data set is actually quite prevalent in a number of different kinds of problems, specifically in scenarios where anomaly detection occurs. So identifying rare diseases, identifying spam mail, fraudulent transactions, there are a variety of different techniques. But the question is, how do you deal with this data? So you've got a credit card fraud example, and you've only got 20 instances of credit card fraud, and you've got 1,000 of none, for instance. And how do you not balance this? So there are different kinds of techniques. One of this is resampling techniques. And the main objective here is to basically balance your classes by either increasing the frequency of the minority class or decreasing the frequency of the majority class. So the idea is that you then end up balancing those data sets. Now your undersampling, your random undersampling, aims to balance class distribution by randomly eliminating from the majority class. So it's pulling instances from your majority class, so it's undersampling it, taking fewer so that it matches the minority class. And this basically done until the classes match. Your oversampling in turn increases the number of instances of the minority class by randomly replicating them to present a higher representation of those instances. All right. Then there's also SMOTE, synthetic minority oversampling technique. And the aim here is to avoid overfitting, which can obviously occur when exact replicas of the minority class are added. So when you look at oversampling, you're basically increasing your minority class. The idea is that that can then lead to overfitting because you're basically duplicating. So here, for instance, a subset of the data is taken from the minority class as an example, and then new synthetic data is introduced. So these aren't duplicates or replicates of what already exists. It's literally introducing new data into your data set that matches the structure of what already exists. Then there's also penalization algorithms, so they're cost-sensitive training. So here is that you increase the cost of classifying mistakes in the minority class. So you're basically setting up your model and you're saying to it, listen, every time that you tell me that it wasn't credit card fraud, but it was, I'm going to penalize you more heavily for it. So you're basically adjusting your cost function to incorporate this kind of a dynamic. Then you also have algorithmic ensemble techniques. This is another way of modifying existing classification algorithms for these kinds of imbalanced data sets. And the main objective of ensemble methodology is to improve the importance of single classifiers. So this basically means constructing several two-stage classifiers from the original data and then aggregating their predictions. So basically what you're doing is that you're incorporating the predictions of the different classifications by using methods like bagging and boosting. I'll discuss that at a later stage. Then I've got one slide on this because Dr. Visaya is going to give you guys an hour's discussion on feature extraction later. But the main idea here is just for you to also be aware once again of the feature engineering component that's important. So, so feature selection or extraction, these are both dimensionality reduction techniques. So when you have your data set and it's too large or you think that there might be redundant information in it, then the idea is basically to just reduce the dimension of that. So your feature selection is for filtering out irrelevant or redundant information. So here the original features are actually maintained. So it's kind of like, I want to classify a dog and I've got information on the tail, the legs, and the eyes. Okay, so the eyes don't match so much, but hey, they need to have specific kind of tail and all of that. So you pull those features specifically out and you're saying these are the features that matter. This feature extraction basically transforms your data to a new feature space and reduces the dimension accordingly. Now, let's get into some actual mathematical models. So I think linear regression is one that's very well known. There are many linear regression techniques, and least squares being the one that's exceptionally well known. So you have input features, and then you've got a specific kind of structure for your model that leads to your output prediction. Your linear regression basically requires that you optimize your in this case, your W, so your coefficients, with the cost function that's usually your mean squared error. So this is very standard. I think at first year level already, you kind of like covered this kind of model. Now, more useful functions can actually be created by then taking linear combinations or a fixed set of non-linear functions being the variables. So this is when you have basis functions introduced. So if you look at this equation, what's happening now, instead of just having an x and x squared like a normal structure, as we did here, we literally have basis functions that are now linear combinations of basis functions that are forming this underlying model. So there are different ways of structuring your linear regression that incorporates more complexity into it. Now the least squares method finds the coefficients that best fit the data, but more specifically, it finds the unbiased coefficients. And what we mean by this is that it doesn't consider which independent variable is more important than another. It doesn't care. There's no feature selection happening. It simply finds the coefficients for a given data set that minimizes the residual sum of squared or the mean squared error. Now, this is where further developments in the field actually came about. So when you're looking at ridge regression, for instance, the cost function is altered with a penalty equivalent. So if you look at the last term that's given here in front of lambda, that's the term that we're talking about here. It basically puts constraints on the coefficients W through this penalty term lambda, which regularizes the coefficient. So it makes sure that if the coefficients take large values, the optimization function is in essence penalized. So in this manner, ridge regression basically shrinks those coefficients and helps the model to reduce model complexity and model multicollinearity. Now, the reason why this becomes useful comes down to one question, okay? Is a model with the lowest residual squared error, so the mean squared error, truly the best model when you're looking at least squares? Now remember, least squares, like I said before, it's looking at the variables in an unbiased fashion. It doesn't differentiate between less important and more important features. Now, this can lead to overfitting a model and a failure to find unique solutions because it's giving validity to features that don't necessarily have it. And it's also leading to multicollinearity. So basically, your least squares model becomes more complex as new variables are added. But what do we want? What we want is the balance between the bias and the variance, and that this must alter until we find that sweet spot. All right. So it can basically be said that least squares model is one with the lowest bias and the highest variance, and in fact, it's fixed at exactly that point. And this is where the alteration proposed by ridge regression comes in, because it introduces this idea of regularization. It's regulating the features in this sense. So that's where your lambda parameter is an impact on your cost function to make sure that the model coefficients can change. So basically, ridge regression then works in part because it doesn't require unbiased estimations, whereas least squares produces unbiased estimates, which could lead to variance so large that they basically become inaccurate. So ridge regression is adding that additional bias, basically just enough to make sure that you're getting better predictions. Now, your lasso regression, also very similar structure. And this type of regularization can lead to zero coefficients. So some of the features are completely neglected by the evaluation output. So it literally can, in essence, what it can do is it can feature select. It's basically helping you in reducing your overfitting. It's feature selecting just through the nature of the cost function structure. So lasso regression is basically also then a linear regression that uses what is called shrinkage, where the data values are shrunk to a central point, like a mean. So it basically encourages a simple or sparse model with fewer parameters. So it's not trying to keep features just for the sake of keeping them. If you look at this visual here, you'll notice that when you're looking at the coefficients for linear regression, they span a much wider domain than they do, for instance, for the ridge, given that those tend to basically pull along the mean, as I've indicated here. And that just shows you how it's got that control over the coefficients. Now, another linear model is called logistic regression. I'm just going to go through this very briefly. Basically, you can take any real valued number, map it onto a value between 0 and 1 through the S-shaped curve. And that's the function in essence that you'll be using. Now, logistic regression is basically a supervised classification algorithm that models the probability of the default class. So in a classification problem, the target variable output y can take only discrete values for a given set of features. All right. Now, logistic regression is a regression model, though. It does actually conduct regression. Basically, the way that it builds this model is by predicting the probability that a given data entry belongs to a category numbered as 1, for instance. Now, k-nearest neighbors, I think this is an extremely well-known method for most. Works for regression and classification. I'm briefly going to go through this one as well. This algorithm basically uses feature similarity to predict values of any new data points. Basically, the data point is a decided value based upon how closely it resembles those in its immediate environment, and how you assess its closeness or similarity is based usually on some kind of a measurable function, so a distance function, i.e. it's very close to these points, so it's similar to them, average them, that's a good prediction value. In a categorical case though, obviously, it's done slightly differently. If the value x and the value y are the same, the distance d will be equal to 0 versus 1. So it's basically looking at more like a majority vote kind of structure. This is just a visual representation of how that would be. In this case, you'll notice that there are 3 lines per predictive point. That's because your k value, your parameter, is indicated as 3. So you're basically telling your model, look for the 3 nearest ones close by and use that as a means of averaging my prediction. Now, this value k, as a consequence, is very important because you're basically saying to your model, which points must I consider in order to be able to get this kind of like an average here, all right? And the k factor basically then is a parameter that completely influences the accuracy, all right, of your model. So for very low value of k, the model is likely to overfit on the training data. All right, so it's basically going to understand the training data too well because it's going to think that this small amount of points that it's referring to, those are the points. In turn, if you have a high value of k, then it's most likely to perform poorly because now it's not really getting a sense for the general patterns that underlie the data set. There you go. Sorry guys, every time something happens on Zoom, then I have to stop for a little. It turns out that there's a certain value of k that's actually seen to be your optimum value, all right? And that's actually can be calculated according to what is the elbow curve. So for different data sets, you can then actually evaluate for a specific k, what is the kind of score? So what is the accuracy? What is the predictive power of your model? And literally then across various values of your k, you should be able to get a curve that looks basically like this. So the idea is that at some point, your k is going to, in essence, have converged to the best value for it to be used within that model, all right? Now, obviously, this is the ideal structure where, in essence, when your k is very small, you're not giving it enough information, so the score is looking, it's not looking, it's either like underfitting or overfitting depending on the k value that you're using, and you want to find that k value that kind of balances score for. Another method which can be employed is grid search technique, which we will discuss a little bit later. I just first want to get through some of the kinds of models that exist. Now under K and N, you also have classification, very similar. Basically, you're just trying to now look at a majority vote. So you're trying to say, okay, based upon what's happening to my nearest neighbors, oh, you know what, most of you are on class 1, so you're going to class 1. That's basically what it comes down to. And again, you have different kinds of distance functions, different kinds of distance matrix that allows you to isolate the neighbors around your point. Now, there's certain considerations for this kind of a method. Firstly, transition from categorical to numerical variables. So there are methods that are capable of converting your categorical values into numbers. And the question is whether you need to do so or use a different kind of learning method. Right? So you've discussed one-hot encoding, for instance. I think Marcel also discussed this with you on Tuesday. And so there are some methodologies where you don't need to do something separate. You can actually handle it internally, but you need to decide as a user which one is more appropriate for your data set. And then there's also standardization of numerical variables between 0 and 1. So if you decide to build a K&N model using a common distance, then you just need to make sure that the features are the same scale, because the absolute differences in the features must refer to the same thing. All right. So basically making sure that you've standardized your variables is extremely important. This is just again an example of your k-nearest neighbors classification, where you're basically isolating your neighbors, then based upon what they are classified as, you classify your predictive point accordingly. Then we also have what are called support vector machines. I think these are also very well known. They're used extensively in the field. Also supervised learning methodology for classification and regression and outlier detection. But it's mostly used in classification, especially two-class classification, works really well. So the objective here of the support vector machine is to find the hyperplane that is the maximum margin in an n-dimensional space. All right. So what basically is happening in this kind of an algorithm is that you're plotting each data point as an in the n-dimensional space, with each feature basically being the value of a particular coordinate. Okay. You then perform classification by finding a hyperplane that differentiates the two classes. I think, in essence, try to just think of having a bunch of Smarties on the floor, and you're trying to put a line down to classify them according to colors. That's in essence what you're doing for this kind of methodology. So your data points are basically falling on either side of this plane that you've created, so that it can be said, okay, you belong to the blue class, you belong to the purple class. So support vectors are basically your data points that are the closest to this hyperplane, and they influence the position and orientation of this plane. So the question then obviously comes down to how to identify this plane. Now, if I had like 5 or 10 Smarties, I'm pretty sure, depending on how they landed, I could just visually look and just put a line down and be like, okay, classify. But obviously in dimensional space, that's not exactly what you're looking at. And you can look at very complex dynamics in terms of your classifications. So this is where you're talking about what are called kernelized SVMs. So a kernelized SVM is equivalent to linear support vector machine that operates in feature space rather than input space. Okay, so you can think of yourself as basically mapping possibly non-linearly structured data into a feature space, and then using your support vector machine there for classification. And the way that this kind of happens is through what is called your kernel trick. Now, I think the simplest way for that, the best explanation I ever heard was somebody saying, imagine if you had different kinds of colored balls, you have a sheet. You take your sheet and you flip it, and all the balls lift up into the air. And in that moment that they're in the air, you then try and move your sheet so that you can classify them according to categories. That movement from the balls being on the sheet and lifting into the air is the mapping. You're basically taking them on a flat surface where you have no idea how to put your hyperplane down. The moment you map them, you've thrown them into the air. Now they have an additional dimensions so that you can more easily visualize where you would want to put the hyperplane. All right, that's in essence what you're doing. You're moving from a space where it's basically not separable, and you're moving to a space where it can become separable. All right, so this is just, again, visualization. Here's a 3D visualization of the hyperplane and how you can put it in place in order to be able to conduct your classification. So this is in essence what the kernel trick comes down to. It's basically your kernel is your function, and this function helps you take your input data into a space where now you are able to actually separate the data according to the different kinds of classes. So when you're training your SVM model, your kernel and its parameters then have a vital role in the classification accuracy. Okay, so suitable kernel design, so that function mapping and its parameters is extremely important in this context. Now, the next thing we're going to look at is multi-class classification. So in contrary to binary class classification, where it's just yes or no, or true or false, or spam and not spam, you're now looking at something that has multiple different kinds of options, right? And you can imagine that this happens more often than not. Classifying an animal, for instance. Cat and dog is not your only option. So one of the probably one of the most well-known examples of this kind of classification methodology is decision trees. Now, these are non-parametric supervised learning methods used for regression and classification, in actual fact, and they can be employed in a very systematic approach. So I've given you a visualization here, and this basically is the simplified idea of what you're doing. You've got a set of questions that you're asking, and in essence, then it starts to learn how to split up the data set. So you have a data set of animals, okay, and you say to yourself, okay, first question, does it have feathers? Yes or no? Okay, then you classify, okay, wolf, yes or no. Now you're like, okay, so fine. So now you're in the category of feathers. Okay, fine. Can you fly? Yes, you can. Okay, you go sit there, and you start, and you basically just move through questions systematically until you've been able to identify, okay, you know what? I now know about you that you have feathers, can't fly, long legs, put your head in a hole, ostrich. Okay. So it's literally just trying to identify the details about that specific kind of category in order to be able to classify it. So in essence, when you visualize it, you're visualizing it like a binary tree. We have a root, and then each of the leaves are your internal roots where a question is posed, and then it splits further into further branches. All right. So the conditional test is then basically represented as that leaf, and then your outcomes lead to your specific kinds of branches. And the leaves of the tree refer to the classes in which the data set is going to be split. Now, a decision tree algorithm then is obviously it's actually a very simple structure. A basic idea is that you select the base attribute using some kind of attribute selection measure to split the records. All right. And you make that attribute a decision node, and then you break the data set into smaller subsets. And this kind of tree building process will be repeated and repeated until all of the tuples belong to some kind of attribute value. There are no more remaining attributes, or there are no more instances. So the kind of attribute selection measures that you can have. Now, your decision tree is basically a greedy algorithm. It performs recursively binary partitioning of the feature space, right? So the tree predicts the same label for each bottommost leaf, and each partition is then chosen greedily by basically selecting the base split from a set of possible splits. So you basically want to maximize some kind of attribute selection measure, whatever that might be. That's your splitting rule. So basically, it's like saying, okay, so I want to decide if you have this attribute or this attribute. I've got some kind of measure, and that's going to tell me which one you most likely belong to. And the attribute with the base score will then be selected as a splitting attribute. So options for this is information gain, gain ratio, Gini index. This afternoon in the practical session, I can actually move through an example with you guys in more detail, because unfortunately I don't have the time to do that here. But in essence, what you're looking at is for information gain, the difference between the parent node impurity, so some kind of measure of its impurity, and the weighted sum of the two child nodes. So you basically want to understand, if I'm moving from this node to that node, which one is going to give me the most information gain? So if I'm standing here, let's say for instance, I am an ostrich. Okay, that's the classification I need to be going to. Is moving towards something that can't fly or something that can fly more information gain? Which one of those should I be moving towards so that I can gain more information and understanding about myself? All right. Another classifier is naive Bayes. This is a probabilistic machine learning model. It's simple, but actually very, very effective and commonly used. It's using the maximum a posteriori decision rule in Bayesian setting. Now, the moment that something becomes too statistical, I think many people start to run. I understand why. But this is actually an extremely useful tool. Understanding the underlying statistics of it can make you be much more effective at utilizing it appropriately. So basically, just think of Bayes' theorem. That's what it comes down to. So you want to be able to understand that given that B has occurred, so some event has occurred, all right? What is the probability of something else happening? That's in essence what all of this comes down to. And Bayes' theorem gives you a relationship between that probability, so the probability of given B that A will happen, it relates it to the probability of A, probability of B, and the probability of given A and B, right? And this is in essence what is being called. The only thing is that there's an assumption that the predictions of the features are independent, i.e. the presence of one particular feature doesn't affect the other, and that's where the naivety comes into this, right? So the goal of any probabilistic classifier is basically that if you have these features, what is the probability of it having a specific kind of class, all right? So probability of x0 to x1 being its features, what is the probability that it's in class CI? It gets used a lot in sentiment analysis, spam filtering, recommendation systems. It's fast and easy to implement, but the only thing is that it does require the predictors to be independent. So this is something you need to be aware of. Just a note, it takes very little explicit training, which is very useful. All that required is that you find the parameters for the features, individual probability distributions, so it can perform well even with high dimensional data and large number of data points. So within the context of classification, you're basically picking the class that has the largest probability. So given all these features, you're figuring out the probability of it belonging to this class, this class, this class. Which one is the highest probability of classifying it into that class? Because that one is the highest probability. All right. And this is basically based on the fact that we use the probability of given A then B as well as the probability of A when conducting this. And there are different kinds of Bayes classifiers. Now, ensemble learning, I'm going to go through this very briefly. Ensemble method basically combines several tree-based algorithms. So we're talking about decision trees, for instance, with the aim of obtaining a better performance. So the idea is that if you took like many decision trees that are weak learners, so they're not the best, but if you're actually able to pull them together, they can perform better as a whole. Think of something like, think of a data set that is quite unusual. So you can find a decision tree that works well in this portion of the data set, but then a completely different decision tree works well in that portion of the data set. Imagine if you could do that and bring them all together. So while it works well in that data set, across the whole data set, this decision tree doesn't work so well, it doesn't look so good, so it looks like a weak learner. But it's still contributing, it's still able to identify something. You want to be able to pull all of the strengths together into one structure. So ensemble algorithms can basically be divided into three categories. The first one is sequential ensemble learning, so boosting. Here, you're looking at an algorithm that principally reduces bias and variance for the supervised learning mechanism. All right. It converts the weak learners into a strong one by generating base learners sequentially, so it does it in sequence. All right. Then you're looking at parallel ensemble learning, so you're looking at bagging. This one is intended to improve the strength and the accuracy of the machine learning algorithms by diminishing the variance. And basically, is this assisting in preventing the overfitting that can happen? Here, what it's doing though is that's creating these different kinds of learners, but it's doing it in parallel. So it's doing it at the same time. All right. Then there's just stacking and blending, and this is usually a combination of multiple different kinds of models. So this is basically if you want to combine models in particular of different types. So neural networks, I'm literally going to go through this very briefly. This is one of the things that this afternoon we will actually be sitting and we'll actually code through it. My advice for you, if you really want to understand a neural network, is to code it from scratch. And there is a lot of code out there, some of it extremely complicated. Don't start with that if this is new to you, but start with something very simple, because it comes across as something extremely complicated. In actual fact, it's like every other methodology we've discussed, it's mappings, all right? So neural networks are multi-layer networks of neurons. You'll see in the next visual image how I put it together. They basically classify items or instances or make predictions through going through a series of mappings, all right? So you've got your input layer, which is where you've got all your inputs on the left-hand side. You've got two hidden layers, i.e. you've mapped it to your one hidden layer through some kind of function approximation. You've mapped it again to a second layer, and then you've got your output, all right? And the arrows that connect the dots show how all the neurons are interconnected and how the data then travels from the input layer all the way through to your output layer. Now I'm going to just discuss a feed-forward neural network, right? Understand there are many different kinds of structures within this context. The moment you go to deep learning, it can become even more convoluted. But in essence, what we're looking at is that these are based on linear combinations of fixed nonlinear basis functions. So your phi j are just your basis functions, all right? And your F that encapsulate this is your nonlinear activation function in the case of classification, and then identity for regression. And you're basically taking these basis functions that depend on specific kind of parameters, which can then be adjusted along with your coefficients, and this is what you're putting through your training process. All right. So they're basically using these basis functions like from that equation, where each basis function itself is a nonlinear function of linear combination of inputs. All right. So what this is doing, again, similar to when we spoke about using basis functions in your least squares, is you're basically saying that you've got a linear combination of nonlinear functions. And that's kind of how you're mapping through. So in essence, your neural network is just a series of functional transformations conducted through various layers via what are called your activation functions. All right, and your activation functions, these are your nonlinear. Now, there's a lot of terminology here, activation functions, etc., etc. But in the end of the day, we're talking about something like a sigmoid function. for instance, things that you are familiar with. This is why when, especially for me, when I wanted to understand this, I literally had to sit down and program it, because the practicalities of it are, they're not necessarily easy. Things in our field are not meant to be easy, but they are much more understandable when you practically start implementing it, because you can see the maths that you actually are comfortable with and you know. Understand a lot of the stuff that we're doing in this modeling structure, the mathematics is known to you, whether it was in statistics or in optimization or wherever it might have been. It's just that now the context is slightly different, and so that can sometimes be quite jarring. So the last few minutes, I just quickly want to discuss model evaluation improvement. This is a very important component, because at the end, you can create a model to your heart's content. If it doesn't perform, nobody cares. So let's just quickly go through some of the ideas that you need to be aware of within this context. The first one is cross-validation. So how do you evaluate your model? Well, like we said previously, you reserve a portion of your annotated data set, and then you test your model on this. Now, if that test data set is too small, then your evaluation is not going to be accurate, right? However, if it's too big, then you've made your training set so small that you probably won't necessarily have very good performance either. So deciding on the appropriate percentage split between your test and your data sets is not an easy task. Now, I once was on a call and somebody was asking, like, what is the best split? Like, people often say 80-20%. 80% of your tests, your set must go to training, 20% test. And the one person said, no, it must be 80-20%. Now, there's no must. Okay? There's no must. There's the problem, and then what's appropriate for that. And there's also making sure that whatever set you're using, that the distribution of the data is similar. Imagine if you took 80%, 90% of your data set for training, and it's got a specific kind of distribution that looks completely different to what your test set is representing. You can't expect good performance on your test set because your data is looking completely differently. So naturally, your model is going to freak out. That's the kind of thing that you check. So I, for instance, structured models where 60% was used for training, 40% for test. Just because I was able to, and actually, it's not just that it gave me the best performance, it gave me the best sense of security in that what my model was doing and what it was getting out of it made sense. So you can't, there's no rule. There is the general trend that people tend to use, but my advice is always that you investigate your choices and you try different options. So what do? Well, you perform multiple evaluations on different test sets, and then you combine the scores from those to get a better sense. So in particular, you subdivide your original data set, right? Just like in this visualization. And then for each of the folds, you train a model using all the data except that specific split. So what you're doing is that you're taking your data set, okay? You're pulling out a piece of it and you're saying, okay, I'm going to use you for testing. I train you on this, now I test you. Okay, put it back, now go again. Take another piece out. You're going to be held for testing. I'm going to train you. Then you're averaging across of these. Okay, so even though the individual folds might be too small to give you accurate evaluation scores on their own, the combined evaluation score is then going to be based on a large amount of data, and that's going to give you a much better sense of what's happening. Okay, so the purpose of cross-validation is not to get one or more multiple trained models for inference, but is to get a better estimated unbiased generalization of your performance. So you want to get a better sense of your performance. So did I perform like this well just because of that specific test data set? Or actually I looked at multiple different test data sets. So actually I know that this is quite a reasonable representation of how my model is. Furthermore, you're able to examine how widely the performance varies across the different training sets, which is also very useful. So if the score varies widely across your different training sets, you should probably second guess your accuracy. If it does quite well, if it does basically the same across all of them, then you probably do quite well. Now, hidden in every set of data is an inherent amount of bias. So depending on how you structured your test or training set, think about this. What you've used to train it is going to bias your model towards a certain kind of performance because this is its world. You've taught it that in this world, things are particular, like basically something with feathers has to be an ostrich. So that's its understanding in that context. So you've biased it towards thinking that anything with feathers is probably an ostrich, right? So you need to always be aware of that. So in essence, it's never going to be perfectly fair. The idea is that you want to include bias to predict certain, you don't want to include as more bias than you need to, given that there already is. So cross-validation basically helps you to try and just balance that out across the board. In your grid search technique, so a parameter is an internal characteristic of a model, okay? And this you can get through your data. So your data will actually help you be able to assess what the parameter value is from your model. A hyperparameter is a characteristic of a model that is external to it. All right. So this can't be estimated from the data. So for instance, the K for K nearest neighbors, right? So given that a hyperparameter can basically be a thumb suck, and often the K is a thumb suck, you're just saying 3, 4, 5. You'd like to have a better way of doing this, and a grid search is in essence how you find those optimal hyperparameters to get better prediction. It's basically brute force. What you're doing is that you are using those parameter values. Let's say you have K going from 1 to 10. You're going to use each one of those, and you're going to check the performance of your model. And in the end, you're going to see, this K value is the one that gave me the best performance. That's your grid search. So you're basically doing a grid search across possible parameter values. Now, that's a simple example. It can obviously become much more complicated. And in order to avoid overfitting through the implementation of this kind of method, you have your validation set that comes into play, which we spoke about earlier, because you don't want to be testing it on your test set, because that can then obviously skew your results. So instead of evaluating the model on the test set during your grid search, you test the validation set. So you're training your model, okay? Then you test it on a smaller validation set, and you're like, okay, for K1, for K2, for K3, you're constantly checking, and you're like, okay, I think K4 is the best one. Now I'm going to test my model that I've created. Right. So grid search with cross-validation, these two tasks are often done at the same time in your data pipelines, where you want to test multiple times, and you want to do hyperparameter tuning at the same time. And yeah, this is just a visualization that you can get from Python, where it can actually show you what is your best parameter setting. So one cross-validation strategy with grid search is nested cross-validation. You see there are multiple different kinds of cross-validation strategies. I just haven't gone into any of them. Just checking the time. So this cross-validation method is often used to train a model in which your hyperparameters also need to be optimized. So you're estimating the generalization error of the model, and then its associated hyperparameters. So you have your inner loop, okay? And that's where your cross-validation that is functioning is responsible for your hyperparameter selection, so your model selection. And then your outer loop is basically your testing, so your error estimation. So it's then testing the model that you've created. All right. My evaluation metrics and scoring, there are many. I think my main comment here is, don't think that there is one way to test your model. There isn't, and don't think that there is that you should only pick one way either. I've been in many discussions, especially with people discussing models that are biased, and they're saying, oh, but this model was so biased, it kept on choosing, choosing specific kind of individuals and saying that they're going to act in a particular way. So it was completely biased against that group of individuals. But then adjust your scoring mechanism. When you're training it, penalize it. Penalize the model for doing something that leads to some kind of bias. If, for instance, your data set is making it believe that, for instance, certain kinds of people are likely to conduct credit card fraud, for instance, right? And you know that that is a bias, adjust your testing so that when your model does make that decision, you adjust it accordingly to make sure that it stops doing that. So there are ways of adjusting your scoring and how you're testing it, i.e., for instance, if you have a model that's classifying whether somebody has cancer or not, simple example, right? Which one is worse, telling somebody they have cancer and they don't, or telling somebody they don't have cancer when they do? I'm going to say the last one because that person might die because of your classification being incorrect. So what do? You set up your model so that if it does that, if it makes that error, you penalize it more harshly. All right, so there are ways of adapting and adjusting accordingly. Now, a confusion matrix is one of the basic ways in which you can understand your errors, and subdivides the errors that are made by your model, which is actually a very nice visualization here. So this is in essence what you're looking at. When you are for binary classification, if you're basically saying you have cancer, you don't have cancer, in your negative class, top left, true, negative, so these were definitely negative. And then bottom left, false negatives. So basically, they were predicted negative, but they actually weren't negative. False positives, top right, bottom true positives, i.e. person did have cancer and was predicted to have cancer, all right? And this immediately can then show you where it is that your model is making the most errors. You can see in this case, there are 8 indications that were predicted to be not 9, but in actual fact, it was a 9. This was an image classification where it had to try and identify if something was a number 9, right? So this immediately then starts telling you and giving your problem context. This is where your problem context is so important. You as a human sit here and say, okay, you know what? I don't care if it misclassifies that incorrectly every 9. That's fine. But this, it cannot get wrong. This is where my accuracy is for me the most important. And that's what you target. All right. So when you're making a prediction for binary, basically false positive, false negatives, you've all heard those. Those are the main things that you tend to worry about. So in a false positive, you predicted an event where there was no event. False negative, you predicted there was no event, but there actually was one. And this is where the context of the problem completely dominates how you want to assess the accuracy of the model. Okay, these are just a few of the different kinds of accuracy metrics. I'm not going to go through them in detail, but this afternoon we can actually discuss them. Some of the concepts you need to be very familiar with is precision, which is the percentage of your results which are relevant. Recall, that's the percentage of total relevant results correctly classified by your algorithm. And then you also have a combination of the two, which is your F-score. This is the harmonic mean between the precision and the recall. Often very useful when you want to take into account both precision and recall. That's usually the score that you tend to look at. Then for visualization of your area metrics, you have your ROC curves and your precision recall curves. Now your ROC curves are appropriate when observations are balanced between the classes, whereas precision recall curves are appropriate for your imbalanced data sets, which is very, very cool. So your ROC curve is basically summarizing the trade-off between the true positive rate and the false positive rate, whereas your precision recall summarizes the trade-off between the true positive rate and the positive predictive value for a predictive model. All right, this is just an indication of where you've actually plotted your precision versus your recall, and you then basically get to decide what is the most appropriate value for you, and then indicator of the model. Then you have your ROC and AUC curve, and this performance measurement is also extremely useful and used quite extensively for classification problems, specifically when you're considering or visualizing the performance of a multi-class classification problem. All right. So the ROC curve is a probability curve, so it's useful when you're predicting the probability of a binary outcome. All right. So your AUC curve, for instance, represents the degree or measure of separability. So how capable is the model of distinguishing between the different kinds of classes? So it's a summary of the model's skill, basically through a consideration of predicting the specific kinds of classes. In your sensitivity, this is like your true positive rate. So the number of true positives divided by the sum of the number of positives. So how sensitive is your model? In essence, it describes how good the model is at predicting the positive class. Okay, so if that is your most important thing for you, then that is the thing that you need to make sure to measure. Inverted specificity or false positive rate focuses on the false positive rate. It's also called the false alarm rate. It refers to how often a positive class is predicted, in actual fact it was negative. So again, this is where if we're talking about the cancer example or the fraud example, you basically decide which one of these matters more to you. In a fraud example, you really do want to know if it was fraud. That is the thing that matters to you more than if it isn't, right? Because nothing bad has happened. So this is again where you as the human decide what is the most appropriate for you to utilize. So model evaluation selection, there are different kinds of ways. So your model, your estimated score, they basically is a score method providing some kind of evaluation criteria for the problem, right? So like for instance, your F-score, your recall, your precision. In a scoring parameter, this model evaluation tools use cross-validation and cross-validation grid search, and then they rely on an internal scoring structure. You'll see that when we're actually doing some Python work this afternoon. And then metric functions. The metric model implements functions assessing prediction error for specific kinds of purposes. So now the default scoring in Python, for instance, is accuracy, but you'll notice that there are many different kinds of methodologies. There are many different kinds of ways of estimating the performance of your model. And I'd really advise that you have a good understanding of the domain in which you're working and what kind of accuracy would be relevant for that specific problem. It's not the kind of thing you just throw an accuracy methodology at it and just think it's going to work like that. All right. So thank you, everyone. that is my presentation for today. I think our next speaker is actually already online, if I'm not mistaken. Terence, are you with us? Prof. Van Zyl?
Yes, can you guys hear me?
Okay, it's very simple.
Can you hear me?
Now we can hear you. Hi, Prof.
Excellent.
I haven't seen any questions, but I mean, I'll be on the chat if anybody wants to ask questions about my presentation. Terence, why don't you start sharing your screen, Prof? We can get you going.
Let me do that quickly.
Sorry, Prof.
There's a place.
Yeah.
Maybe after, maybe
Okay.
during.
I'll go on to the, oh, is there a question in the room? Sorry, guys. Terence, while you're sharing, I'm just answering a question in the room. Yeah, sorry.
Okay, one of the slides is when you show the training set, the validation set, and the test set. Okay, I thought if you are doing cross validation, it shows that your training set is used for the cross validation, just like you explained. Some parts will be trained while some will be tested on, and then the average will though in my thinking, I thought, since you said that if we make it 90-10, it will not be good enough. Okay, so why making it small 90-10, another small 90-10, and then averaging it, and we still say is good, it will be good. When if normally, if you share your data set into 90 and 10, it's not good, except maybe 30, 70, 60, 40, just like you
Why is
mentioned.
90-10 not good?
The training set is too small from
It
one of
depends
the
on the
slides.
size of your data set, remember. It depends on the distribution. 90% training and 10% test can work. Seen it before. It's very
In most literature, that is not recommended.
Mostly what?
Literature, that is not recommended.
Yeah,
Yeah.
but
And I've not seen
that's a generalization.
someone
Yeah.
recommending that or doing that
Yeah.
yet. Yeah. So what I'm bringing out is that, okay, in the training sets and from the picture you show, we have the training, we have the validation, we have the test set. Okay, if we are doing cross-validation, are we not using the training set to do the cross-validation? Are we still doing training, then doing another one for validation, then before the test set?
Yes.
So what is the
This is gonna
percentage
be a
here?
conversation,
Yeah.
so let's continue with Prof's slide and then you and I'll chat during the break. Sorry, colleagues, the discussion is about the test versus training versus validation set. So we're going to take it. If you have any questions, please just post them online and I'll answer them. So our next speaker is Prof. Terence Van Zyl. He is a professor at the University of Johannesburg in the Institute for the Future of Systems and in fact also the Nedbank Research Chair. So thank you for being with us, Terence, and we look forward to your presentation.
Thank you. Can everyone hear me clearly? Maybe just a little nod or something, just to make sure. You good? Okay, I'm just going to assume that I can be heard. Yes, so I'm Professor Terence Van Zyl. I'm from the Institute for Intelligent Systems here at the University of Johannesburg, and I currently hold the Nedbank Research and Innovation Chair. So over here you can see we recently acquired this little spot robot here at the Institute for Intelligent Systems, and with some applications around that. And I'm quite an avid climber, I enjoy rock climbing. And if you want to have a look at some of my recent work, that's a URL, and you'll be able to find my email address and other ways of getting hold of me over there. Just in terms of what exactly the Nedbank Research Chair is, it's a collaboration between Nedbank and the University of Johannesburg with the intention of bridging the gap between academia and industry, specifically in this case, the banking industry, with the idea being that we take some of the learnings that we have from academia and find a mechanism to transfer that into industry. And in the same way, take some of the real world challenges that they have in finance and the banking industry and try and transfer those back into the academic space so that we can start dealing with these real world problems. And to those ends, we look at things like obviously research, but also stuff like master classes and webinars and the likes of these types of things. Okay, so today what we're going to be talking about is the portion of machine learning that's known as unsupervised machine learning. And so it's quite a big field, and it's a bit of a mishmash of a field because a lot of stuff gets lumped inside there, and it doesn't have as clear a process associated with it in terms of a workflow associated with it, as you would see in supervised machine learning. Also, a lot of the outcomes in this space are qualitative rather than quantitative. So it's a lot more difficult to measure whether some sort of unsupervised learning has been successful or not. But what we'll do is we'll just start by taking a quick recap on what is machine learning, because we want to understand how is this unsupervised machine learning going to fit into the space. So in this most general kind of way of thinking, given a question of the form, is this a cat or a dog in machine learning? And given some experience, so some past experience in the form of data, what we will typically say is that the machine learns if it's able to improve at the task. So in this case, the task was answering that question, is this a cat or dog? So we have a very broad view on what we say machine learning is. You can see that a lot of stuff can fit into this framework. Any time that you have some sort of data, and that data doesn't necessarily have to be offline data, it could be online data, observations coming from sensors in sensor streaming or whatever it might be. Anytime that we have some data and we have some task that we want a machine to perform, no matter what that task is, if the machine can take that data and improve itself, then we say that it's learning. Okay. This would contrast, for instance, a classical computer program, which typically the code is written once off. And so as good as it was when you wrote it, that's as good as it will always be. So to this end, we have a little bit of sort of terminology that we're usually using. We say we're training the machine when we are showing it some experience, so the data for training. And typically we're using the word testing to say that did it improve at that specific task. And all of this makes a lot of sense in the supervised learning paradigm. And that's why I've presented it right now, because we want to contrast these two things against each other, unsupervised and supervised learning. So in the supervised learning paradigm, you can see it makes a lot of sense. Our pipeline in supervised learning is we start off with a data set, we split it into 2 or 3 portions, depending on how we're going about it. We do a certain process to arrive at a set of model parameters and a set of hub parameters using the test, the training and validation sets. And then finally, we take this third portion of our data, the testing set, and we go and assess the quality of that learning. And this process, the test set, implies that we actually have a way of determining whether or not the model was good or bad. So there has to be some sort of label that says this was a good model or this was a bad model. In this case, we would know the truth about this thing. This is a dog or this is a cat. So we know that truth. And so it's possible for us to put together a nice test to determine whether or not this machine has learned anything. Unfortunately, and also true of the real world that we exist in, not all data comes with truth. So a large portion of our data doesn't have the labels associated with it. So imagine now that you've just got this pack of photographs and most of those photographs don't have any labels on them who the person in the photograph is. Okay, and someone says to you, okay, go sort these. So this changes the task a little bit, because before it was possible for you to know whether or not what you were doing was right. You could go and look at the actual labels. You could actually go and train this thing and you'd be like, okay, yes, it got this person's name correct. I know this model is right. I've got this target to work against. Okay, so in those cases, the supervised learning cases, we usually have some sort of baseline truth. It doesn't always have to be labels. It could also be numbers. It could even be a vector representation. So the truth might be a vector. Say, for instance, you're trying to do segmentation of an image and you want to segment out some cancerous region or some anomaly in the human brain or whatever it might be. That could be your target, but you have this truth. You actually know what the truth is, and that allows you, one, to do the training, but two, also to do the testing. And so you have now a sense of how good that model was. In some instances, we actually have some labels and then a whole lot of data that's unlabeled. And what we've learned is that more data is always better. And so we want to come up with ways of using the data, all the data that we have available to us, even the ones that don't have labels. And so the semi-supervised learning space tries to tackle this challenge where we have some data that has labels available to us, with those labels are numbers or vectors, arrays, or even as simple as a binary classification. We want to use those alongside the data that has no labels associated with it. So that's our semi-supervised learning space. And this is a very active area of research. It makes a lot of sense because you can bring an expert in and get the expert to label a bit of the data, not all of it, and then get a whole lot more other unlabeled data and bring these two together. Then you can try to benefit from the labels that you have from these experts, plus all this additional data that doesn't have any labels associated with it. A third area of machine learning, as we're sort of moving towards where we're heading, which is this unsupervised learning, is this area of active learning. And yeah, the actual machine learning algorithms tend to be a bit more active in their process of acquiring labels. So it might say to us, listen, this label over here is a label that we would like to acquire because we're not so sure about the specific piece of data. We're not sure which class it belongs to. And so in those cases, we have this sort of active learning. I'm going to skim over reinforcement learning. It's not really in our space here today, and jump to where we're going to talk about, which is the space of unsupervised learning. So in certain instances, we have data with no labels. So we know no truth about the data, but we still want to do something. Now, the strange thing is that humans actually operate quite extensively in the unsupervised learning space. So biologically, we're quite effective at acquiring new knowledge without having specific labels for things. And there's a number of tricks that we take advantage of, and it also leads to a number of human biases. But largely speaking, what we're looking for is we're looking for some sort of correlations in time or space when it comes to humans, or some sort of similarity in terms of attributes. So we're looking for things that are similar, and if we can find some sort of similarity between things, we can start grouping them together in some way. And this is one of our process of organizing the world around us by saying, okay, all of these things are green, all of these things have leaves, all of these things seem to behave in this certain way, they're passive in their interaction with us. Okay, these are plants. And we can group them together broadly and say those are part of one group. And then these things over here, they're fluffy and they run around and they lick you in the face. And so these things, we're going to think of them as dogs, say, for instance. And so we have this mechanism of grouping the world in that way. Interestingly, you can see that humans actually, in terms of our interaction with our parents, play around somewhere here in this active or semi-supervised learning space, because often what we're doing, a young child will be saying something along the lines of pointing at something and saying, is that a dog? And then the parent might correct the child and say, no, that's actually a cat. And so that's this process of active learning. And you'll see with children, they get quite obsessed with certain new topics as they try to embed that idea in their head. So they'll keep on pointing at helicopters for a week or whatever it might be, as they're trying to affirm what exactly helicopters are and how good they are at recognizing helicopters once they've sort of managed to separate them from the rest of the things flying in the air, birds and helicopters and so on and so forth. So we know that unsupervised learning is possible. So it's possible to learn without labels. And so the field of unsupervised learning is largely geared towards trying to see what exactly can we do here, how can we benefit organizations, how can we improve science, how can we improve people's lives, businesses, etc., using data that doesn't have labels. And you can imagine that that's also economically makes sense, because gaining labels for data is an expensive process. So it involves a lot of time in terms of resources of experts. I mean, imagine if you're trying to do like some sort of cancer application and you're trying to get examples of tumors in brain, say, for instance, you need experts to sit and say, this one does have one end, this one doesn't have one end, so on and so on, and there's a lot of ethics and stuff around that. So there's a lot of resources that go into trying to get labels. And so obviously we're interested in this unsupervised space as well. Okay, so then the question is, how exactly do we learn without labels? Because when I started out our conversation, I said, well, we've got this training data, and then we've got this testing data. And so that implied that in order for us to determine whether or not our model had improved, so that was one of our criteria for learning, was we said that with experience, it got better at the task, we would go test it. And so in order to test it, we need to know the truth. And so you can see immediately here we have sort of an impasse in the field of unsupervised learning. And so at this point, I tell you that there is no way for us to test it in the classical sense. Instead, we need to have these qualitative measures of how good unsupervised learning is. And you can see this sort of in the style of testing that has to happen and the type of metrics that you'll see in the space, and even the whole area of research makes it a lot more challenging. Actually, it's a more difficult space to do research in. It's a lot more easy to do research in a space where you have a clear target. You got 80% accuracy, I get 85% accuracy, my method is better than your method. But if we're operating in a space where we don't have such a clear metric, and we now need to qualitatively determine whether or not my segmentation of an image is better than your segmentation of an image, then it makes the research a little bit more murky. And so it makes the progress in this space not as rapid as we've seen in the supervised learning space. Okay, the first way that we're going to try and organize our thoughts around this, this question of how can something learn without data is to talk about two very important topics in the space of machine learning, but that in themselves are not 100% agreed upon by everybody, but we'll try and get to the most commonly agreed upon understanding of these two concepts. Okay, so these two concepts are discriminative versus generative models. Now, the easiest way to think about that sort of, as a starting point in terms of your thinking and to take us forward a little bit in our conversation this morning is that discriminative models discriminate and generative models generate, okay? So what do we mean by a discriminative model discriminating? Discriminative models are the classical models that we find in the supervised learning space, okay? So what you'll do is you'll build this model. Here's our model over here that we built, able to recognize dogs and cats. And what we will do is we'll now pass it a picture of a dog, and it will discriminate between it. It'll say, okay, this thing is closer to these blue guys over here, and I have a boundary that tells me that anything that's on this side of my boundary is definitely a dog, and so I can discriminate that this is a dog, and that's discriminative learning, okay? And so if this came in and it landed up on the yellow side, it would say this is a cat, and we would say, ah, you're wrong. And so this model's accuracy would go down. So this is a discriminative model. It's able to discriminate. Now, the interesting thing, being able to discriminate between cats and dogs doesn't necessarily mean that you actually have a model of the distribution of cats and dogs. So you don't necessarily have to have some sort of understanding of the probability distribution of what cats and dogs are, nor do you even have any knowledge about how to generate a cat or how to generate a dog. You just have to know how to separate between the two. And the mechanism for you to do that might be very arbitrary. Maybe you decide that if the picture is taken on a couch, it's more likely that it's a cat. If it's taken, on the lawn, it's more likely that it's a dog. You might have these very arbitrary features that you're using to create this discrimination that don't mean that you necessarily understand the difference between cats and dogs, but it does it does result in very high quality models that are very practical in the real world. So this discriminative learning is very, very effective when we're trying to do things like classification or regression. Now, another style of learning that we might use is generative learning. Now, the main idea here is in generative learning is that we're able to build up a probability distribution over the entities, dogs and cats. So now we actually know what the distribution of dogs looks like, what the distribution of cats looks like. And so because of that, we're now able to sample from that distribution. So we can go and sample from the distribution. And as a result of being able to sample from that distribution, we can actually go and get ourselves a dog, a new dog that never existed, or a new cat that never existed. We can go and sample from some place in this distribution and get ourselves a new dog or a new cat. So you can see in this generative space, suddenly there's a whole lot of very interesting things that can happen that weren't available to us in the discriminative space. And we can use these generative models for discriminative tasks as well. But their real value sits here in this, in the ability to generate instances and also to start understanding other attributes about instances like the density of them, so how similar are them, how dissimilar are they from other classes and the likes of these things. So the majority of unsupervised learning happens in this generative space, generative model space of some sort. Okay, and especially the modern unsupervised learning. And what I'm talking about here is things like variational autoencoders, which we'll touch on a little bit, generative adversarial networks, which we'll touch on a little bit. These are all unsupervised learning mechanisms that are sitting in this generative space of models. Okay, so that's the sort of first piece of information that we want to sort of hold in our brains as we're moving forward in trying to understand how exactly we can go about learning without labels. Okay. So in the slide over here, we're basically just trying to formalize that a little bit more. We're not going to go into heavy formalism of sort of the mathematics of this, but we're just trying to get a feel for where do all of these pieces sit together. So the classic one, supervised learning. These are our discriminative models that we saw, the ability to recognize the difference between a cat and a dog. And over here, usually what we're trying to achieve is we're trying to learn a model which can give us the probability of y, that is the label. So is this thing a cat or a dog, given some data x? So given a bunch of attributes, maybe an image, what is the probability that this thing is a dog or a cat? These are our discriminative models. They're sort of the probability of y given x. And so in this case of we can go off with these models, and we can learn to assign labels to data. And typically this is in our supervised learning space. As we had mentioned before, there was no way for us to generate new data from these discriminative models. We can say what the labels will be, but we can't generate new instances in this space. The interesting thing about the Bayes rule is it contains the other pieces of machine learning that we want, the other unsupervised pieces that we want. On the left-hand side here, we see the conditional generative model probability. That's the ability to give us an instance of X, the probability of some X, given a label Y. So given that I want a cat, it can then say to me, well, I'll generate a cat for you. So you can see that it can generate that cat for me. Or we could learn the unconditional generative model over all of the data. And the interesting thing about this one is that once we've learned this unconditional generative model, so the probability distribution over all of the data, we can start doing things like detecting outliers. So anything that doesn't sit within our probability or has a very low probability of existing, given the label that we're interested in or just in general, we can now start saying that's got to be an outlier. This thing doesn't fit into the distribution that we have. Whereas with a discriminative model, it doesn't matter with our discriminative model that that this dog was all the way down here in the bottom left-hand corner, far away from our decision boundary. It will still tell us that's a dog. It won't highlight to us that, no, that dog over there is way outside what we expected. Whereas if you look at this generative model, if we gave it a point over here, it's possible for it to tell us, listen, that's way outside of our expected distribution of what dogs or cats should look like. And so we can start flagging that thing, for instance, as an outlier or as an anomaly, for instance. So already now we're starting to see two kinds of things we would be able to do with generative models. If we can build up a model, an unconditional generative model over the data, and we don't need these labels for it, we can do one, we can generate new instances of entities from that distribution. And two, we can now start detecting things like outliers. So we can already see two types of things that we would be able to do in an unsupervised manner without labels. Okay. Obviously, it's also possible in this conditional framework of here to actually say, okay, well, let's imagine that we want to build up a general model that can generate all animals, and then we can take the distribution with respect to some specific label, and then we would be able to say, okay, let's generate a cat or a dog from that model. Okay, so we can see the pieces over here, and it also tells us something else that's quite interesting, which is that it will, by rearranging these components here, it will be possible for us to build a discriminative model from the generative components. So given that we've learned the generative components of this model, we would then be able to build a discriminative model as well. And so sometimes you will see supervised learning as part of, as a generative model as well. There's certain methods that are generative models, and then they'll say, okay, but it's still a supervised learning model. And that's because we can still rearrange these components. But if you just learn the discriminative component, it's not possible to generate new instances of that. So that's a very broad and high level understanding of what do we mean by generative versus discriminative models. And the reason we've done that is because we're trying to unpack what are the kinds of things that we can learn in an unsupervised way when we don't have these labels. Okay. So what are a few other things that we can do? Well, one thing we might decide to do, so we've already touched on the anomaly detection, okay? And we've already touched on this top right-hand corner over here, things like generative adversarial networks and variational autoencoders, the ability to create new samples that never existed before. But there's a few other things that we might be able to do in this unsupervised paradigm. For instance, if we replaced Y, well, let's start with clustering. One thing we might try to do is we might try to say to ourselves, can we go and find a set of labels that never existed before? So can I go and find a set of labels Y in this paradigm. And so what I'm effectively doing in clustering is I'm taking my data and I'm saying, okay, if I look at this data and I organize it in certain ways, can I find labels for parts of that data that are grouped together by some metric of similarity or some way that I believe that they should be grouped together? So I might say, let me go and find some labels from the data, and I can use maybe distance or something like that. I can also go and say, well, maybe I don't want to just have a label. I actually want to have a vector representation, so some Z, some intrinsic dimensionality, some intrinsic representation, yeah. And then the question would be, can I go and find an intrinsic representation of the entities? So in this case, I'm not trying to learn a label. I'm actually trying to learn an entirely new representation of the data. And so in that space, we see things like manifold learning or similarity learning and autoencoding. Some of these methods are supervised, but we're going to touch on the unsupervised versions of that. We've touched on anomaly detection and change detection. Another interesting thing that we might do is try to see, has the probability distribution of a specific instance changed? So has it moved within this space? So these are a few of the things that we might be able to do in an unsupervised manner. Some of the more modern ones are generative adversarial networks. They come from variational autoencoders. These are underpinned by a long history of density estimation. Clustering is a very, very old field. Association rules is a form of clustering, but with the intention of trying to overcome some very high computational restrictions on this problem space. Change detection, maybe being able to check whether there's been a change between two images. So you've got one image of someone's brain, another image of someone's brain. Can you spot the change? Or you've got two pictures of the Earth. Can you spot the changes there? Or you've got two time series. Can you spot a change in those time series? Anomaly detection, looking for instances within a time series or within a set of data that are outside of normality of that data, so outdown of the expected distributions, and then the ability to generate new representations of the data, so not generate new instances, but new representations. And these new representations might be valuable for numerous reasons, from the fact that they might be in a lower dimensional space, so we may be able to overcome some of the curse of dimensionality by moving into a lower dimensional space, or they might be more explainable actually in this lower dimension, in this new representation. So we might have had the original image and we've moved it into this new space where it's a lot more explainable, for instance. So there's numerous reasons why we might want to build new representations of the data. And also sometimes these new representations can help us with our clustering to do better clustering as well. So these are a couple of the things that we're going to discuss over the next half an hour as we try and dig into them. Obviously, we don't have enough time to sort of get into the as deep as we'd like, but what we want to do is have a sense of what are all the possibilities, what are all the things that are available to us in machine learning that we could sort of go learn a little bit more about and take that and apply it in our specific domain. Okay, so the first one we're going to touch on is the space of clustering. Now, previously I said that the nature of unsupervised learning is that determining whether or not we've done it well can be quite qualitative. And you can see here this example right at the top here. One person might have decided to cluster this into 4 clusters and done that by color. Another person might have decided, no, actually, I'm going to cluster this into 3 clusters and I'm going to do that by shape. Now, neither of these answers is wrong. And depending on my use case, I might decide that this one's better or that one's better, or I might come up with a completely different one, which might be, based on a combination of the 2 attributes, so try to cluster them together, or something else that I see in these images that other people don't see, say, for instance. So maybe I decide I'm going to put all the things that have sharp edges together and all the things that have no edges into another cluster and cluster it into 2 clusters. So there is no right answer here when it comes to this idea of clustering. Unfortunately, good clusters are going to be things that are clusterings that are most useful to us at the end. broadly speaking, we have, there's maybe a few more of them, but these are the 4 big mechanisms that we might go about trying to do clustering, okay? On the left-hand side, we've got these similarity-based approaches. I mean, typically what we're doing over there, we're saying things that should be in a cluster together are things that are similar to each other, measured by some attribute of similarity. In the previous slide, we had color, or we had shape, and I went on even to talk about sharp edges. So these are attributes of similarity. And so in the similarity-based approaches, what we'll typically be trying to do is we'll say, okay, if these 2 things are similar to each other, they should belong in the same cluster. And if they're not similar to each other or dissimilar, then we should put them into separate clusters. And over here, you can see would be an example of a whole lot of points that we're trying to move into clusters. In the centroid-based clustering approaches, what we'll typically do is we'll say, we know how many clusters are in the data. So we might say, okay, we know there's 4 clusters here, so we want you to find us 4 clusters. So we're going to create these 4 centroids, and these centroids are the center of all of these points in their specific cluster. And so what the algorithm will try to do is it will try to assign points to a cluster in such a way that, and usually this is the sort of rule of thumb thinking about it, is that all the points in the cluster are more similar to each other than points in another cluster. So what we're trying to do is minimize the distance between points in a cluster and maximize the distance between clusters. So within versus the without distances. Minimize the within distance while maximizing the without distance. That is a computationally intractable problem, because trying to iterate over all of the different combinations for all possible clusters would just take a massive amount of time. And so usually we have some sort of rule of thumb algorithms or greedy algorithms that allow us to find good clusters in a much shorter amount of time. Another approach that we might take to this is to say, okay, let's not have specific centroids, let's keep track of all the clusters. And so usually in the connectivity-based or the hierarchical-based clustering, what we will do is we'll actually try to keep track of the entire hierarchy of data points. And so then we don't have just 4 centroids, we actually have all the centroids. Now, this is a difficult one because now, you know, we've kind of kicked the ball all the way down the road to the opposite end. We don't actually have any clusters, we just have the structure that organizes all of the data. We still need to go in here and say, okay, I'm not going to split at this level, I'm going to split at this level. And so that's going to give me vertebrates and invertebrates as my way of splitting up all of my data into these 2 clusters. There's 2 main approaches that we go about doing this, agglomerative and divisive. In the agglomerative processes, we start out with every single data point sitting in its own cluster. And then what we start doing is we slowly start grouping them together. So we take 2 points that are closest to each other and we make a new cluster from them. The 2 next points that are closest to each other. So we construct these and then we say again and again, and we slowly move up. So we're agglomerating them from the bottom up. And that allows us to create this hierarchy. And the mechanism for measuring the similarity between 2 points can be something like Euclidean distance, but we might use the Molinovis distance. We might have an outside similarity measure that we've been given some sort of ranking, for instance. We might have a similarity matrix that we've generated. So that notion of closeness or similarity is defined by the domain. Another way in the divisive approach to this is that we start out with one big cluster and we slowly start splitting it into 2 and 3 and so on. We slowly break it down, starting from one big all the way to the end. And then typically what we will do is we'll pick a threshold at some point and say, given that threshold, that allows us to split this data into X amount of clusters. Now, what's quite interesting here is you can see that in this, we had to predetermine the number of clusters that we want based on the number of centroids. Over here, we don't have to say how many clusters, but we still need to pick a threshold. So inevitably, we have one of these free variables or parameters lying around that we need to set. These are what we refer to in the supervised learning space as the hyperparameters. So we've got some hyperparameters that we need to set. Okay, so those are the similarity-based approach. Another thing that we might do is try and look for dense regions in our space. So go and look for areas that are of high density and group those together and say they make a cluster. And that's quite natural for us. A lot of the time, if you present it with data, you will go and say, oh, here's one dense region, here's another dense region, and you'll say, okay, those are two clusters. So often we're looking for these dense regions in two-dimensional space, because that's what humans, well, I suppose we can operate in three-dimensional space. We could find these clusters in three-dimensional space based on the density of points in those spaces. And so those are typically your density-based clustering techniques. They're going to look for dense regions. And so everything that's sitting in the dense region, they'll put into a cluster. And you can see what's quite nice about these density-based approaches is that we can start picking out outliers, points that aren't part of any of these regions. Also, you can now start to see where the intersection between our earlier discussion on generative models and clustering is sort of starting to touch on each other, because one of the things is that once you can build up a good density model, so once you can build up a density estimate, then you in effect have a generative model. So now a good density estimate allows you to get some sort of generative model, and so you would now be able to go generate new points from inside this density space, and you would be able to start detecting things like outliers after doing clustering, say, for instance. In the third approach, what we try to do is take a more statistical based approach. And so we say, let's assume that the data was not just some arbitrary density, but that it's generated from a specific set of distributions. So that there's a set of probability distributions. Most of the time, these will assume to be Gaussian, and a classic example would be like a Gaussian mixture model. And so we assume that the data is generated from those. We can use something like expectation maximization or whatever it might be to go and find the three Gaussians that best describe this data. And so once we've got those, we can then assign points to those, and we say, okay, this is one cluster because we know they belong to this distribution. This one's sort of a slightly more, this is a round one, this slightly more oval distribution. But it doesn't have to be Gaussians, it's just they tend to be a little bit more tractable in the space and easier to reason about. And so a lot of work has been done in these sort of using Gaussian models here. So these are the four big approaches that we have. There's also some fuzzy approaches that are used for clustering as well. But you can sort of get a sense of what we're trying to do when we're trying to cluster. Either we're working with how similar is the data in terms of distances or Euclidean distances, or we're trying to say, is there some probability distribution that generated this data, and can we find the parameters for that? Or we're trying to say we're looking for dense regions in this Euclidean space, and we believe that those make up clusters. Okay, so if you took a tool like scikit-learn, you'll see that it has, I don't know what's this, a whole lot of different clustering mechanisms. And what's interesting is if you scan through these, you can immediately see that, you know, not all of them work well in every situation. And we call this the no free lunch theorem, actually. But there is no free lunch here. There's no one method that's going to work in all situations. So we see dbScan works really well. dbScan is an approach, works really well on these circles. It's able to split out these two different manifolds. It gives us some points. It does very well on these three Gaussians, and even if they doesn't mind whether they're ellipsoids or if they're very circular. But you can see here in this bottom example, it's not able to split this one out at all, and who knows whether that's right or wrong. On the other hand, if you looked at something like k-means, which is a centroid-based approach, you can see that it doesn't do well on these complex manifolds at all. It doesn't do really well when you've got a mixture of Gaussians that overlap each other. It does good on these sort of individual circles, which all of them seem to do well on, and it's able to come up with some sort of a way of splitting up this block of data over here into what seems to be reasonably equal portions. Then if you had to look at some sort of a method like the hierarchical clustering, like the agglomerative clustering over here, you can see that it does well on the manifolds. It actually does quite well in the mixture, but it's not doing so well when you've got these ellipsoids that have been generated. So there is no one best clustering algorithm, but on the whole, DBSCAN is really good. DBSCAN is really good. Optics is good. Both of them are able to pick out those outliers for you. But for instance, maybe you do really want to have a hierarchy, and so you might pick something like agglomerative clustering, or very interestingly, if you look at the speeds here, you will see that something like k-means is really, really fast. So if you're after a really quick clustering, and it's not important how accurate it is, you might, for instance, pick something like k-means. That's my time. I'm going to skip over this example, but I'm leaving it in the slides so that you guys will have them available to you. And I want to move to this deep clustering framework, just one little slide, just sort of to touch on this idea quickly. So up till now, almost all the ones we've looked at are algorithms that are squarely within the sort of traditional machine learning, computer science space of doing clustering. But there has been a lot of work recently at trying to use deep learning to do this clustering as well. And some really interesting algorithms in the space: it's deep embedded clustering, deep clustering networks, Joule, and DAC. So these are all examples of deep clustering frameworks. And typically what we have in these deep clustering frameworks, you'll have some clustering loss, we'll have a network loss and a deep neural network. And the idea is to try and learn a representation of the data. So that idea that I spoke about earlier, like having another representation of the data that is more amenable to clustering. So it's quite difficult to do clustering on images directly. But if you can take the image and you can represent it in a nice one-dimensional vector, an array of values, and that vector representation has preserved the original information that was in the image that you have, then you can go and use your classical clustering on that and cluster those images. And so a lot of these mechanisms at first tried to do these in separate steps, and then more recently, more effort has been put into actually integrating them into one step, so that now the learning of the representation and the clustering steps, so the learning of the representation will be up here and the clustering step are happening simultaneously as it's going through the data and trying to find those clusters. Okay, so I've been touching on this topic of representations for a little while, and so I'm just going to dig into what exactly a representation is in a little bit more detail. The important thing about a representation is the real world is not amenable to computers. Computers work with RAM, and that RAM is blocks of memory locations that are filled with numerical values, specifically binary numerical values. And so the real world and computers have a little bit of like a mismatch between them. And so what we want to be able to do is find a way of taking the real world into our computer space. And if we can move it into that computer space, into our digital space, we can use our digital algorithms, the likes of k-means or whatever they might be, to work on that data. Now, not all representations will be useful. So what we need to do is we need to preserve certain things about the real world in our representation space. The classical unsupervised learning way of doing this, probably 20, 30 years old, maybe even older, don't quote me on that number, is manifold learning. The one most known to us is in the nonlinear manifold learning space is principal component analysis. Principal component analysis is unsupervised, and it's a way of taking data and applying a linear transformation that gives us a new representation in which we've exposed certain characteristics of the data. In this case, specifically, we're exposing the directions of maximum variance. And that also allows us to reduce the dimensionality of the data by throwing away those directions that aren't valuable to us. And so previously I touched on the fact that having reduced dimensionality can be very useful for machine learning algorithms. And one, for explainability, and two, also more tractable in terms of computation. Now imagine this was our data, this S over here, sitting in some two-dimensional space. What we would like to be able to do is project this into, in three-dimensional space. We want to project this into two-dimensional space. And we know that this S is sitting on what is known as a two-dimensional manifold. We can see that it's sitting on this two-dimensional manifold. And so we know we can reduce its dimensionality and preserve all of the information that's inside here. And so these different manifold learning methods try to do that. You can see MDS, multi-dimensional scaling, kind of gets a little bit of it right, but it's kind of like just squashed it onto the two-dimensional plane. SE, it's done okay, but it's lost one of the dimensions. But we can see some of these other ones like LTSE, ISOMAP. They've actually been able to unpack this S really nicely into our two-dimensional space. So we've now gained a new representation. And now in this new representational space, we can see that the distances between 2 points are more accurate, say, for instance. So 2 points that, if we took a point red on the S here and on a blue point, then those points would be actually close to each other in this three-dimensional space because they're sitting on this manifold. In the three-dimensional space, they're sitting directly apart from each other. But if we measure them with respect to the S on the actual manifold, then those 2 points can be quite far apart from one another. And so sometimes being able to uncover the underlying manifold that the data is sitting on allows us to get a more accurate representation. So that's the first type of approach. One way that we might do this with neural networks, and this is quite an interesting thing to do, is that we use this little trick, which is to try and reconstruct the data after squeezing it through a bottleneck. Over here, you can see over here, we might have what's known as a classical autoencoder. We have the encoder part on the left-hand side. We would have a decoder and some squeezed latent representation. And so we feed the images, and this doesn't have to be images. I've done this with many, many different types of data in the past. We squeeze the data through on the left-hand side. It goes through this bottleneck, this squashed latent space. And then we try and reconstruct the original image from this latent representation. And so you can imagine now what it has to do is try and get as much information about the original image, which was this massive 64 by 64 bit image, into the small latent representation, say 8 bits, say for instance, and then try and unpack the original image from that. And so in that process, we now know that a lot of information about the original image is sitting in this bottleneck. And so we can use this now, this latent representation for clustering, for instance, or we could use it in other machine learning tasks. Say, for instance, we're working with a model that doesn't take as input images, it takes as input vectors, maybe a support vector machine. We could pass this latent representation into the support vector machine, say, for instance. And this can be done in a completely unsupervised way because we don't need any labels. We just need to reconstruct the original data. So this is the idea behind autoencoder. There's variants on this. Some of them try to enforce sparsity on the latent representation. Some of them try to add noise to the input image. Another thing that we might do is try to use Siamese neural networks, so two neural networks, to try and find things that are close to each other. And the trick here in this space, how we make this an unsupervised task, is we exploit what humans exploit in the real world. So we would give two things the same label in these Siamese neural networks if they're close to each other in the real world. So say, for instance, you've got a map of a city, two buildings that are close to each other, we would say, okay, those things get the same label. Two buildings that are far away from each other, they don't get the same label. So we're on the fly assigning labels to things to our data. You can see unsupervised learning or visual representation from image patches using locality. You can use the location within an image. So you can say, if I've got a picture of, say, for instance, some landscape, that two areas that are close to each other, they're probably the same thing, like forest and forest. Two places that are far away from each other, like building and mountain, they would get different labels. So that's another way that we might go about trying to do unsupervised learning. And I've put a whole lot of little links over here of these 4 different papers over here, 4 different major approaches in this space. Okay, touching on generative models. I think one of the big progresses we've made in recent times in machine learning is the ability, specifically AI actually, is the ability to generate art and the likes of these things. And so I'm just going to, here's this thing. Oh, well, here's an example of it. So I had nice ones on a website I wanted to show you, but I did cut and paste 2 in here. So these 2 humans' faces, these 2 humans do not exist. Okay, a generative adversarial network has been trained in an unsupervised way to learn how to generate instances of human face, pictures of human faces. And so we can now take that model and get it to generate a fake face for us. And the way that we do this in a generative adversarial network is we have a generator and a discriminator. So we've seen that. And we get the generator to try and generate a fake image. And we have some real images of humans, so ones that have been seen before. And the discriminator tries to predict whether the image that the generator generated is a fake or true. And so slowly but surely, the generator gets better at generating fakes, and the discriminator gets better at identifying the difference between fakes and non-fakes. And so the end result of this is that we have a generator that's able to generate really, really good fakes. And the kinds of things that, I mean, if you think of the complexity of this, of the probability distribution to generate an image of a person's face compared to like kernel density estimators that we're using in the past, the generative capability of these models is massive. And the kind of applications, we haven't really even started to understand them. I mean, there's a lot of bad applications like fake news and the likes of those, but there's going to be a lot of very valuable applications now that we can actually generate such realistic real-world data. Okay, touching on the sort of last little slide over here, I just want to talk about some unsupervised applications in general. So yeah, I've touched on this idea of change detection. So we can use unsupervised learning to, for instance, detect changes between 2 images. For instance, we could either use an autoencoder to do that. We could use build representations that allow us to do that. So there's a number of approaches to that. Anomaly detection is another massive space that we can use unsupervised learning in, other than the clustering that we've seen. We've touched on the idea that if you build up some sort of distance or density, then it's possible for you to identify those individuals that are outside of that probability distribution. So if you have a generative model, a distribution that represents the data, that's possible to identify those that sit outside of that. There's decision tree or random forest-based approaches, which I'm not going to touch on, but are worth mentioning because they're actually very, very effective. And then there's approaches like the deep learning approaches, such as an autoencoder. For instance, remember I told you before, we tried to get the autoencoder to learn how to reconstruct its input to its output. And so what we might do in those instances is that we can actually measure after it's been trained how well it can do that on a new image. So we give it an unseen image that it's never seen. If it's not really good at reconstructing it, we can flag it and say, it obviously never learned how to reconstruct an image like this. And so this obviously, this image, well, obviously, but this image likely falls outside of the distribution of data that we have. And so we're going to flag that one as an anomaly as well. So that sort of brings us to the end of the things that we wanted to chat about today. I know it got a little bit more rushed than I liked at the end there, but they're all very interesting topics. And I'll be happy to take a few questions if anyone's got any.
Good morning.
Morning.
Yes, thank you so much for the presentation. My question is, all that you have been talking about, how can they be carried out? I'm actually new to machine learning, and as much as some of the concepts described are, I mean, at least I have some understanding, and as a way of introduction to machine learning, in my mind, I'm just thinking, how can they be carried out? I mean, how can they be performed? How can they be practicalized?
Mm-hmm. So I mean, most of these models that exist, there's open source versions of them. So any of those like generative adversarial networks, it's possible for you to go to a library like PyTorch, and you'll actually be able to pull in those libraries quite quickly. We've actually done that recently. So many of those models exist. And then some of the other stuff like the clustering side of things, libraries like scikit-learn have all of those clustering techniques built into them. So the clustering libraries do exist in scikit-learn. Things like the anomaly detection is already in tools like scikit-learn, and things like, for instance, the generative adversarial networks, they're a lot more difficult to get traction on, but there's definitely examples that you can use out there. Here's an example of a person's face that doesn't exist. How cool is that? Does that answer your question?
Well, I would have to check out some of the information given.
I think that's a good place to start.
Yes, thank you. Please, can you put the link? I mean, the source links to some of those materials in the chat to
Okay,
ease.
I will do.
Thank you.
Happy. Hi, Terence, we have a problem. Our data has a lot of variables relative to the number of observations. How do we reduce the dimensions, and how do we need to do that? How do we need to do that before clustering? Okay, so all of those manifold learning techniques that I spoke about, those are very effective at reducing the number of dimensions. So I would start with those in scikit-learn and try to reduce the dimensionality. Also, like I mentioned, those isolation forests, random forests also have a mechanism, some mechanisms, but I would start with the dimensionality reduction techniques in scikit-learn, reduce the dimensionality. And actually the first place I always start is just with simple principal component analysis. So I would just start with PCA, reduce the dimensionality there. Obviously it's not all of the, I suppose yours is a bit tricky, and I understand you can't use PCA. So look at the MDS and those techniques within the manifold learning techniques, because some of them are capable of handling high dimensional spaces with a low number of instances. In the cases where the variables are categorical, I think that in the random forests that you will be able to find some mechanisms to deal with those categorical variables, XGBoost and the likes of those tools. I think that's all our questions.
Yeah.
Here's a person who doesn't exist. Here's a cat that never existed before in the world. It's quite something. You can go and look at these sites. Just type in, this person does not exist, or this cat does not exist, and you can get examples of generative models. I can't hear you, Sharice.
Thank you.
Now I can, yes.
Can you hear me now?
Yes, I
Okay.
can.
Thanks very much. Are there any other questions here in the audience? I don't think we have questions this slide either, Terence. Thank you very much. I don't see anything on the chat. But I promise to give everybody your email address so you can get bombarded with questions. All right.
Excellent. Sounds good.
Thank you so much for your time. I really appreciate it. Have a good
Okay,
weekend.
thanks, guys. Cheers, eh?
All right. So for those of you online, we will be back again at 11 with our last presentation for the week. And for those here, let's grab a cup of coffee. Thanks, everyone.
Thanks.
Morning, everyone. Welcome back to those of you online and those of you in the venue with us. We have our final speaker today, is Dr. Vivian Versailles. She also spoke on the first day, and today she's going to actually not just expand on what she discussed then, but actually take further what Prof. Sale and I were talking about earlier today. So thank you very much for your presentation, Vivian. We look forward to it.
Thanks, Cherise. So as the last speaker, I'd like to thank everyone who stayed in June online, and here in person. And I'm sure Prof. Cherise is going to thank everyone, all of the organizers later on. So if you listened to the Monday and the Tuesday, even the Wednesday talks, there were a lot of mention of feature selection, feature extraction. In fact, when Prof. Cherise and Terence were talking, and even when Marcel was speaking, I was just thinking, what am I gonna present on today, since most of the topics have been already discussed. But I think it's good to hear, things again. Okay? So the topic is on feature extraction. So this is usually, this usually addresses the problem, and I know you've heard this a lot, of the curse of dimensionality. Okay, so what you want is, with a lot of variables, what you want is to only pick those that are important for you, maybe prediction in your model. Okay, so dimensional reduction, as have been previously mentioned, is just reducing the number of features in your original data. Okay, and this is done in two ways: either feature selection. Okay, so among all of the variables, choose just a subset of that. Either you reuse the variance threshold, or lasso regression, or logistic regression that was previously discussed in the first talk. Okay, so this is removing unnecessary features, okay, and only focus on the important ones, so that computationally it's good. Okay, so it decreases computational cost, and maybe hopefully in some cases improve the performance of your model. Okay, right. So feature extraction. So just this, I just want to put it out there. I'm not a machine learning person, but I'm trying to understand or work on this field, and incorporate some of what I know in, say, time series analysis or dynamical systems. Okay, so for feature extraction, okay, what you want is to transform the data into new features, okay, by finding a smaller set of variables. And this variables is usually a combination of your original variables. Okay, so these are the two feature extraction techniques that we know, PCA. It's been always mentioned in talks, and I think I want to go over this method, and later on add some or incorporate some of what I discussed on Monday. Okay, so TCA and LDA, principal component and linear discriminant analysis. Okay, so for PCA, the idea is to transform a large set of variables into a smaller one, but that still contains most of the information in your large data set. Okay? So the reduction may come at an expense of accuracy, but you gain simplicity. Okay? And we know that if you have a simple, smaller data set, then it's going to be easier to explore, easier to visualize, and easier for faster, easier maybe to make your machine learning algorithm faster. Okay, so these are the steps. Okay, you standardize your variables so that they're all comparable, so that biases can be removed by those with large ranges. Okay. Number 2 is to compute the variant matrix, compute the eigenvectors and eigenvalues of your covariant matrix M, pull out the feature vector, and 5 is to visualize your data again, using these new components that you've computed. Okay, so I'll just go through the steps very quickly. So this is the reason why you have to standardize your variables. So I put here continuous variable because this was asked in the previous talk. It was a question to the speaker. What if you have your variables is categorical? Okay, I didn't quite catch the answer, but that's also the reason why I'm putting continuous variables, because usually PCA, I've worked on it, but only on continuous variables. I know for categorical. So if you have any ideas, you can put it down in the chat. Okay. All right, and it's easy to standardize. This is the usual formula. Okay, so for those in the workshop, students in the workshop or students listening, it's very important that you standardize your variables, because I see, students, our students applying their projects on some data set, not even doing any pre-processing of the data, particularly standardizing the data. Okay. Right. Next is the covariant, the construction of your covariance matrix. Okay, so if you have P variables, if your data dimension P, your covariance matrix is just Mij, which is the covariance between variable I and variable j. And we know that the covariance of a variable with itself is its variance. Okay? So the only thing that matters here really in your covariance matrix are the signs. Well, not the only thing, but what's important to look at in your matrix M are the signs. Okay? If it's positive, then the two variables are correlated. Negative, they're inversely correlated. Okay, right. So this is where most of our linear algebra come in. Okay, so it's important not just to know your statistics, okay, but go back to your basic linear algebra concepts. Okay. All right. So for principal components, okay, remember, okay, these are components that are mixtures or combinations of your original variables. Okay. So see this one. So for the eigenvectors and eigenvalues of M, okay, let's see, what do we do? What we do is the following. Okay, we compute the vectors and then eigenvalues of M. Okay, and then there are interpretations to this. Okay. Okay. So what PCA does is to try to maximize the possible information in the first component. Okay. So what you want is for everything to be, all the information of your data be in the first component, okay, and the rest for the succeeding components. Okay. Okay. So geometrically, okay, once you get this vectors and eigenvectors and eigenvalues, okay, we have the following interpretation. The principal components, okay, the vectors represent the directions of the data where the variance is maximum. Okay. So this line captured the most information of the data. Okay, so the idea is that the larger the variance carried by the line, the larger dispersion of the points along it, and the more information that is captured there. Okay, so now from your original data, you now have your PCs, your principal components. Okay, so to get these principal components, we go to this slide. Okay. All right, so eigenvectors of M are where the direction is has the most variance, and the eigenvalues, they give the amount of variance carried in each principal component. Okay, so what you do is once you've computed the eigenvectors, okay, you rank them from highest to lowest, and then compute their eigenvectors. Okay, so the highest, because the eigenvector associated to the highest eigenvalue is your first principal component. Okay, the second one, your PC2, and so on. Okay, all right, so computing the eigenvectors and ordering the values in descending order allows us to find the PCs in the order of significance. Okay. Right. So the goal here is just the following. Okay. We want to reduce the dimension of the data, but okay, if you only seek to describe your data in terms of the new variables, there's no need to exclude some of the variables or some of the components. Right, so now that I have your PCs, PC1 or PC2, PC3, okay, how would you visualize your new data? Okay. So the final step here is as follows. Okay. The final data set is just the vectors that you've chosen, okay, times the standardized original data set. All right. Okay, so this is an example that I'm going to work on later on in the workshop. Okay, for those who are here, okay, we have the Wisconsin breast cancer data set. Okay, so it has 569 data points and 32 variables. So given as follows. The ID is actually the tumor ID, okay, and the rest are the following. The diagnosis is either B, benign, that's non-cancerous, okay, or M, malignant, which is cancerous. Okay. So if you want to do like prediction here, your output would be Y equals diagnosis. Okay, so given all of these other variables, can you predict whether tumor is benign or malignant? So this is the PCA of the breast cancer data. Okay, you can see that, you know, even if it's high dimensional, 31 or 32 dimensional, in 30-dimensional space, okay, looking at it in this 2D space, okay, PC1 and PC2, okay, gives us you know, good visualization. Okay, we can see that, you know, the reds, the M's, they cluster in one side, and the B's cluster on the other side. Okay. So this one is the data that I introduced on Monday. It's a marmoset data that I work with some colleagues. Okay, so it's just really analyzing admixture in the data of marmosets. Okay. And our data here are so this is just, you know, a quick discussion because I've already discussed this on Monday, but, you know, analyzing it a different way. Here it's the PCA. Okay, so haplotypes are good trackers of lineages. Okay, again, each marmoset, it's a type of monkey that we study has 2 haplotypes, and the haplotypes are just these SNPs. Okay, sequences of single nucleotide polymorphisms. Okay, so we have N equals 100 marmosets and M equals 167,000 length of SNPs. Okay, so in this example, it's just 10. The length of the SNP in this example is just 10, but we worked on, in this example, 167,000 length of SNPs. Okay. All right, so this is the graph, the PCA plot of this marmoset. Okay, so I just have to mention that this I didn't generate, it was my collaborator who generated this. Okay, so he's the one who has all of the computational power to do this. Okay, but you can see clearly that the PCA analysis shows that the colonies of marmosets are genetically distinct. Okay, so in this case, I think due to some data privacy, I can only show the plot of genetically distinct colonies. Those marmosets that were admixed, I can't show. So it's different with math where you can just show lots of data. Here I had to ask permission. Okay. All right. So so essentially that's the PCA that we know. And I think we have to really know because at some point we forget about it. Okay, so the next method of another method of feature extraction is called linear discriminant analysis, or LDA. Okay, so it's same, it's on dimension reduction, but the goal is to preserve the separation between the classes that is also present in your data. So if you have an idea, that your data is has clusters or is in classes, but then using PCA, it doesn't really appear there. Okay, so maybe what you have to do is LDA. Okay, so this is the opposite of a linear regression, okay, which I'll mention later. Okay, so what it wants is to keep as much separation or discrimination among points as possible, hopefully reducing the complexity of prediction. Okay. So this is an example where this is the data. Okay. So using LDA from 3D to 1D is the following. Either this is the worst 1D subspace, but the best one would be this, right? So if it's just one-dimensional, it still shows, preserves the clusters, the separation or the clusters of your original data, which you see in 3D. Okay. All right. So as I mentioned, it's the opposite of linear regression. Okay. So this was already discussed in the previous talk. What linear regression is, everyone knows about it. For LDA, it's a max-min algorithm. Okay, so it maximizes the distance between boundaries or line to the data points, but at the same time, it minimizes the distances between points themselves. Okay, so sometimes I think that the term here is a max-min algorithm. Okay, all right. So this is just in connection to what I discussed on Monday on feature extraction. Okay, so this is using topological techniques to extract features from your data. Okay, just a quick overview of what softwares are used. Javaplex, you have a high dimensional data, that's your input, and your output are just these barcodes, these numbers, a begin and an end. Okay, so it's a sort of well, it is a feature extraction technique. Okay, so even if you have 100-dimensional data as input, okay, what you have are summaries. Okay, H0, it tells you the number of clusters of that high dimensional space. H1 tells you the number of holes, okay, in that high dimensional space. So even if and H2 is the number of tunnels. So even if you only see 2 or 3 numbers here, okay, for H1, some begin at the left endpoint and end at the right endpoint. Okay, it's still something that gives an idea of how your underlying high dimensional space look like. Okay, so this is another well, this software again. It's the mapper algorithm. Same, the input is a high dimensional point cloud data. Okay, but you have to specify filter function, covering, how many covering, and even the metric on X. Okay, so all of this really have some mathematics behind it, but at the end, once you use the software, it seems easy. Plug and then output, but you really have to understand the math, okay, what's happening, so that you can choose the right parameters, the right metric, okay, and the right filter function. Okay, so this is the same breast cancer data, okay, that where we used Mapper, okay, as a tool to analyze the data. So, it's quite different from the PCA visualization. Okay, so for the PCA, it only clusters the M and the B. Okay, but in this case, you can see that there's more clusters. Okay, so here, I use the Kepler Mapper software. Okay, so this is, okay, hold on. Okay, let me just show you how the Kepler works. Okay. Oh, sorry, I thought it was open. Okay, I'm on it. Okay, where are we? Okay, give me a second. I'll just show you Kepler. Okay, so this is yeah. So we generate here the we just run it. Okay, so the input here, anyway, there's a Python code for this, of course. And then I don't know if it's going to show it, but yeah, there. Okay. What happened?
Are you sharing screen or sharing application?
Sorry, I'm just sharing this. Yes. Okay. It's better. Right. So this is the result for Kepler Mapper. Okay. So you can get the summaries of this network, okay, and even the cluster details. You can play around with this, as long as you have an idea of what the good parameter values are. So just really play around with it. All right, so let's go back. Okay, so it's always that, we can use this type of tool as an exploratory data analysis tool, okay, for clustering, either for feature selection or extraction. And even for statistical, predictions, you can use this qualitative results to input in your quantitative method. Okay? So the idea here is to use these structures that you get from Mapper or JPlex or barcodes, in particular the loops and the flares, okay, to identify interesting clusters, features, or variables in your data. Okay. All right, so next is the application to time series reconstruction. How do you, extract features of your data? Okay, so here we work on the calendar data. Okay, the thing is, how do you distinguish the structure of something that's deterministic, okay, and something that's maybe stochastic? Okay, so a calendar data, what we do is just construct a sequence, okay, of numbers coming from a calendar, sequences that fall on a Monday, followed by sequences that fall on a Tuesday, and so on. Okay, so there is a pattern in your sequence. Okay, so do delay reconstruction so you can have an idea of how the space looks like in reconstruction space. Okay, so from that sequence, if we reconstruct in 2D or 3D, and by reconstruction here, I think it's different from the reconstruction of machine learning. I'm not sure for those who are ML people. So what we have here, if we reconstruct this data in 2D or 3D, you can see that there are clusters, nice clusters. Okay. If we extract the clusters using barcodes, it's obvious also that there are 7 clusters. Okay, so the barcode structure for B naught, the number of clusters that appear here is 7, okay, which I guess corresponds to the number of days. Okay. Right, so that's nice. It's a nice figure. Okay. But what if your data is not determinist, it's not nice? For instance, the generated data. So this one is just an experiment that we made using the result here, okay, by Motorola and others. Let's say that individually, humans cannot generate random numbers, but the random sequence is produced by stitching the numbers generated by at least 7 individuals. Okay, so this is in a physics journal. I don't know how they got those numbers, but it's in a reputable physics journal. Okay, so therefore you have this 99 numbers gathered from 99 people. Okay, what do? Do you append? So I get 99 from you, and then just include the 99 from the next, and so on. Or okay, we alternately stitch the numbers generated by the individual. Sorry, 99 number 7 individuals. Okay, so all the first that you generated, followed by all the second that you generated, and so on. Okay, so that's another way of getting a long sequence of data from this 99 times 7 length data. Okay, so you can see here, obviously, that it's not as nice as the reconstructed space or structure from the calendar data. Okay, all right, so the next one is financial data. Okay. Okay, so what type of financial data did we work on? Okay. So I'm just presenting all of this because what I'm saying is that it can be applied to any type of data, basically. Okay, so the data is the stock USA DJI, okay, and it's taken from the 23rd of November 1987 to the 29th of September 2017. So we have a time series which is length 7,504. Okay, so what's nice about this data, this time interval, is that it contains what they call the dot-com crash, okay, which happened on March 10, 2000. Okay, so how do we extract any topological structure here, okay, that can say something about the crash of the dot-com crash? All right, so this is not a nice figure, but if you plot the data, it doesn't look nice. The time series would probably just look like that. Okay. So what we do is to work on sliding windows or segmentation first. Okay. So what we do is divide your time series into windows. In this case, we use window size 50. Okay. And for each window, we do reconstruction. And once you have reconstruction in a suitable space, high dimensional space, 2 or 3, you compute the barcodes. Okay, so that's the first one. Choose a window, construct in the high dimensional space. Okay, and then, okay, sorry, maybe you can skip the fourth one. Okay, but later I'll tell you that Well, there's a theorem that says that if you take a certain percentage of your original data, okay, the structure of that subset will be the same as the structure of the original data set. Okay? So once you have your set, you compute the structure. So these are the results for the topological structures of the windows. Okay, so the B naught, the number of clusters is really not interesting. It's always one. Okay, so which means that whenever you take a window and reconstruct it, okay, it's just always one cluster, right? But if you notice for B1, so B0, there's no interesting thing happening. But for B1, if you notice, okay, so this line over here is when the financial crash happened. Okay, so if you look at what happens to the holes before the crash and after the crash, it's sort of consistent. Okay, so as you approach the crash, okay, there's something happening to the holes. It's decreasing. Okay, and after that one, it would increase. Right, so something happens to the structure of your data, okay, at the crash, and that structure is captured by the holes. Okay. Okay, so how do we use these topological structures, okay, to machine learning methods? Okay, so recently there's this term called topological machine learning. Okay, so it essentially uses the topological structures that you get from your topological methods to improve accuracy of machine learning algorithms. Okay, so we apply this to the alphabet data. So now we have images. Okay, it's a classification problem. So this data comes from Slate, the study by Slate in 1991. So we identify, so the data consists of 17 variables, okay, where one is the label of your data, and the other 16 features are the horizontal position of the box, pixels, of course, vertical position, width of the box, and so on. Okay, so these are the images of letters, how you write letters. For A, it could be small a, or script, or calligraphic, or whatever. Okay, so there are 16 features that they extract from images of letters. Okay, and it consists of 20,000 entries. Okay, so these are your letters. So at least there's no letter that dominates the data. Okay, most of them are about 700. Okay, right. So what we did here is the following. Okay, so we got this 20,000 entries, which are of course randomized. Okay, and took subsets of those entries, subset of the data, and performed barcode analysis. And once we have the barcodes, we took the statistical barcodes of these 12 features. Okay, so the first feature would be the mean of when a feature appeared. Y is G2 is the mean where a feature disappeared, and so on. So mean, median, and standard deviation of when a feature appeared, when it disappeared, and their difference. Okay, so as I mentioned a while ago, okay, even if you have a very large data set, okay, sometimes, okay, using some nice math that support this technique, you can just take a subset of your big data set, okay, and then work on that smaller data set. Okay, and there's a theorem here, the homology inference theorem, okay, that states that with some ideal, parameters. Okay, whatever you have, the L, which is some percentage of your large data, okay, will have the same topological structure as the real data. So L, which is a subset of your bigger space, will have the same topological structure of your bigger space X. Okay, so from my Monday talk, it's really different from the Takens embedding theory on series reconstruction. Okay, but it's the same. It's the same idea. Okay, you can work on something simpler, less complicated, and whatever you get there will have the same structure of the more complicated underlying space. Okay, all right. So this is these are the results for the 3 machine learning methods that we use. So Prof. Harley already introduced this: ANN, SVM, and KNN. These are the ML techniques. Okay, using 20,000, all of the 20,000 data set. These are the accuracy. Okay, so here what performed best is the KNN. Okay, if I only take a subset, say 13,000, okay, so the accuracy is not too bad. Right. Now, what we do is we add some topological feature in my original features. Okay, those 12 statistical barcodes that I mentioned a while ago. So we added that, okay, to the original data set, and we get the following accuracies. Okay, so if I only get 20% of my 20,000 data set, can you see? Right. So if I only take 20% of 20,000, okay, then the numbers are low, right? So yeah, even 40%, if half, I won't take that. But once I start increasing the percentage of the total number of data points, they start increasing. Actually, here, even if it's just 20%, they start being around 90%. So in this case, those topological features, okay, do give larger accuracies. Okay, right. And this one, I just leave it here because I have not analyzed it yet, but we also tried to, we used, each letter, data of each letter, okay, those 700 plus, okay, and try to put that in mapper. In this case, I am only showing 2 cases, letter S and letter V. Okay, so the output for mapper is this for letter S, and for some reason V, it looks very complicated. Okay, this is the output for letter V. Okay, so again, this is a 16-dimensional data as input. Okay, and what you're getting is just a network, which is 2D. It can be 3D, okay, but it doesn't mean that you've reduced your data. This is just the information, okay, of 16-dimensional structure. Okay. I think that's it.
Are there any questions in the audience? If there are any questions online, just put them in the chat or unmute yourself, please. Looks like we don't have any questions, but we'll still be online for a bit for those of you that have questions online. I just like to, as a final word, just say thank you very much to everybody who's been here with us in person, and also thank everybody that's been with us online for every one of the days of this workshop. The second week is going to only be focused on those individuals that are here in person. We will have various kinds of problem structures that we would have put together, and then basically the methodologies that were discussed during the week will now be used as a means of solving those real world problems in infectious disease modeling. So I just want to thank you, all of our presenters, all of our speakers. Thank the audience. Specifically thank everybody from the Department of Mathematics and Applied Mathematics here at the University of Johannesburg, especially Prof. Farai, who's the head of the department. Thank you very much for all your contributions during the week, and we look forward to the second week. Thank you, everyone.